Welcome to Iron Wolf Academy's Aligned AI for EEE course. Our goal here is to help you build autonomous hardware that continuously learns without sacrificing safety or operational efficiency. Across 15 sections and 21 slides, you will gain 3 key capabilities. You will learn to engineer microchips and sensors specifically optimized for tight AI constraints. You will also discover how to apply adaptive models to power grids while enforcing strict stability guarantees. Lastly, you will master deploying fully embedded decision loops that keep your data private and your devices functional, even without a cloud connection. By the time we finish, you will be equipped to bring intelligent, secure systems to life. Welcome to Module 1, where we examine the physical foundation of artificial intelligence. To truly grasp how AI functions, you have to look beyond the software and examine the underlying machinery that powers it. Standard generic processors were never designed to handle the massive and unique computational demands that AI demands. That is why specialized hardware architecture has become an absolute necessity. Throughout this module, you will learn why traditional computing falls short and why custom-built hardware is required to drive modern AI capabilities. Understanding this physical layer gives you the essential starting point for everything else we will cover. When you are building at this level, hardware is never an afterthought, it is your primary constraint. Every physical choice on the silicon is dictated directly by your software requirements. If your algorithm demands high bandwidth, that need dictates the exact memory bus width you must specify, or the entire chip fails. You do not just throw parallel cores onto a board either. They only exist if your signal processing truly requires simultaneous execution steps. Even traditional principles like circuit isolation take a back seat. Today, the physical layout of the chip directly mirrors your AI data flow. Your algorithmic requirements are literally shaping the hardware. Think of the stage as building the system's nervous system. Just like your own brain processes sight and balance at the exact same time, our neural network has to digest completely different sensory inputs simultaneously. We achieve this by splitting the workload based on the nature of the data. Spatial depth is handled by feeding LiDAR point clouds through convolutional kernels, while movement over time is captured by streaming IMU gyroscope data straight into recurrent memory cells. The crucial takeaway here is sensor fusion. By aligning these distinct spatial and temporal receptive fields right at the start, before training even begins, you give the network a single, coherent picture of reality. When you build for edge devices, physical reality always wins over theoretical performance. It does not matter how accurate your neural network is on paper if it drains the battery or generates enough heat to burn out the sensor running it. As engineers, your design process has to start with energy and thermal limits. You must aggressively shrink your models down so they can actually survive operational conditions. That requires a fundamental shift in mindset. Stop optimizing solely for top-line accuracy metrics and start fitting your AI directly to the physical hardware constraints of the real world. At the end of the day, physics dictates what actually works. Building a physical foundation requires a true co-design approach. If you aren't designing silicon around your actual AI workload, you are essentially creating expensive glass. To avoid this, your schematic capture needs to begin with a clear definition of your computational bandwidth requirements well before you start drawing transistor paths. At the same time, look at your sensor interfaces. They must align precisely with the sampling rates your adaptive filtering loops require. Finally, tackle your thermal budgets immediately. If you wait, you risk running into heat constraints that force you to cram simplified, downgraded models onto high-performance hardware that was built for much more. Now we move into Module 2, where we focus on signal intelligence. Traditionally, signal processing relied on hard-coded algorithms and fixed mathematical rules. While that works well in predictable environments, modern data environments are far too dynamic for rigid formulas. This module is all about shifting our mindset and our tech stack. We are taking those deterministic systems and evolving them into adaptive, data-driven frameworks. By integrating intelligence directly into how we process signals, our systems learn from incoming patterns, automatically adjust to changing conditions, and extract far more meaningful insight. This transition is critical for building resilient infrastructure that scales intelligently as data complexity grows. Standard linear algebra works great on paper where precision is infinite, but your actual hardware operates under strict FPGA clock cycles and physical limits. When you rely on traditional filters with fixed coefficients, you are using a rigid system that completely ignores what is happening to your hardware state in real time. The moment you push past those physical boundaries, fixed constraints break down. Adaptive filtering solves this by monitoring your system continuously. As soon as you breach a physical threshold, adaptive algorithms dynamically recalibrate their parameters on the fly. Instead of failing under stress, an adaptive approach keeps your entire system operating safely within its bounds. When you modernize legacy signal processing, there is a critical trap you need to avoid. Traditional linear blocks provide guaranteed stability margins that keep your operations predictable and safe. However, when you remove those standard linear components and replace them with dynamic alternatives, you lose that mathematical safety net. Picture a standard PID loop. The exact moment you switch that controller over to an adaptive neural net, it forfeits its phase margin. Without those hard stability guarantees, the entire system becomes vulnerable to unpredicted behavior. Upgrading your signal intelligence isn't just about swapping in advanced algorithms. It is about recognizing the fundamental stability margins you forfeit when you walk away from legacy linear processing. When you switch your pre-processing pipeline from fixed coefficients to recursive least squares, you fundamentally change how your system handles biomedical signals. Biological data changes constantly, and static rules simply cannot keep up. By using adaptive filters, your system tracks those non-stationary signal shifts dynamically in real time. This allows your models to automatically filter out biological artifacts, separating them from actual physiological events without manual intervention. Crucially, executing this inference locally means you eliminate the need for external network calls, achieving the millisecond level latency required for live critical monitoring. It keeps your processing fast, precise, and entirely self-contained right where the data is generated. Now we move into Module 3, where we focus on what we call the edge loop. Here, the goal is all about bringing intelligence directly to the hardware operating on the front lines. In many deployment scenarios, you are working with devices that have strict resource constraints, whether that means limited processing power or tight memory capacity. This module addresses how you actually implement local intelligence on those constrained systems. By shifting processing directly onto the device, you eliminate the delays of remote processing, allowing your hardware to achieve true real-time autonomy. It ensures your system can evaluate and act instantly right where it operates. When you run AI directly on your local device, you completely redefine how your system makes decisions. By cutting out the network, you eliminate round-trip delays. Local decisions happen instantly because your device never has to pause and wait for external approval from a server. Beyond speed, removing cloud reliance gives you total resilience. Your core functions keep running smoothly, even if the surrounding network fails entirely. This local edge loop is where your circuit breaker logic comes into play. It allows you to handle failures right at the device level, dealing with the immediate breakdown locally rather than relying on a distant root cause to fix itself. Relying on the cloud for critical split-second decisions is a fundamental mistake. Consider a pacemaker. It simply cannot wait for a remote server's permission before triggering a heartbeat. In the real world, when your internet connection cuts out completely, your device has to be capable of making instant, critical choices on its own. By running AI models directly on local hardware, you guarantee continuous safety and reliable operation, even if the system never connects to the cloud again. While network-dependent platforms experience catastrophic failures the moment connectivity drops, embedded AI is built to survive and keep functioning safely in those exact high-stakes moments. When you are running inference on edge devices, the physical limitations of your hardware dictate everything. A highly accurate model is useless if the device overheats and shuts down. To survive these resource-limited environments, you have to adapt your architecture. First, you prune weights, aggressively cutting down the model until it fits strictly inside your available RAM. Next, you apply quantization, lowering numerical precision so tiny processors can run inference quickly and efficiently. Finally, you use knowledge distillation, using a large teacher network to train a smaller student model that can actually operate on constrained hardware. Ultimately, making the model fit the physical device takes priority over everything else. When we talk about the edge loop, privacy isn't just a software setting or a policy update, it is baked directly into the architecture. By physically separating your compute capabilities from the network, we create a natural firewall around your data. Because all the processing happens locally on the device, raw inputs never touch a network in the first place. This deliberate design choice guarantees that sensitive information simply cannot leave your hardware, keeping intelligence confined within that physical boundary. You aren't relying on extra rules or permissions to protect user privacy here. You are using the fundamental structure of the system to ensure that private data never has the opportunity to escape. In Module 4, we turn our attention to safety and ethics in the grid. As systems become more independent, automation must never come at the cost of security or compliance. The goal here is simple but absolute. We must guarantee that autonomous optimizations never violate established safety constraints or privacy laws. Throughout this section, you will see why setting these strict operational boundaries is essential. We need to ensure that every automated decision respects physical limits and protects user privacy at all times. By embedding safety and legal compliance directly into our grid processes, we build an intelligent system that you can trust to optimize performance responsibly. When you build predictive maintenance models for the grid, you cannot rely solely on healthy baseline data. To catch issues before they happen, your training set must capture actual pre-failure signatures. If you look closely at historical current waveforms, they reveal subtle harmonic shifts happening long before a complete breakdown. By including these specific patterns in your data, your model learns to tell the difference between a heavy normal load and the early signs of thermal stress. That distinction is what makes the system truly proactive, delivering predictive alerts days ahead of a catastrophic installation failure, so you have time to safely intervene. When you deploy AI systems in the grid, you have to plan for what happens when the information stream completely cuts off. It is easy to assume these models will always operate without limits, but in reality, actual systems fail the moment data stops coming in. That is where safety and ethics become critical. When you face severe data scarcity, you are forced into a tough trade-off. Do you prioritize keeping the system running, or do you dedicate resources to continuous learning? A truly intelligent system cannot depend on a constant flood of inputs. It must be designed to remain safe and operational even during the silence. When you write code for autonomous grid systems, you have to remember that it executes on real copper and silicon, not in an abstract vacuum. That means software decisions have immediate physical consequences. Because of this, hard safety constraints are non-negotiable. While soft optimization goals like fine-tuning performance are important, they must always step aside the moment physical limits are threatened. By enforcing deterministic stability guarantees, you ensure the grid behaves predictably and stays safely within its boundaries. Ultimately, these rigid rules exist to prevent catastrophic hardware failure. When physics demands action, safety protocols must always take absolute priority over optimization. When you take autonomous grid control to regulators, you run straight into a fundamental conflict between how AI operates and how the law is written. Existing regulations were designed for deterministic machines, systems that follow explicit, predictable rules without making AI-style mistakes. AI, on the other hand, is probabilistic, which creates the single biggest legal hurdle you face today. Regulatory bodies will not accept a system that is usually right. They demand absolute proof of safety before approving autonomous decisions. To get these systems cleared, you must design an architecture where probabilistic errors are mathematically impossible in your most critical operational zones. What you see here is the entire foundation of Iron Wolf Academy. We keep our core model remarkably straightforward. The focus is entirely on building autonomous hardware that continuously learns, while making sure we never compromise on safety or operational efficiency. Too often, people assume that adding adaptability to hardware means accepting higher risks or lower output. Our approach eliminates the trade-off entirely, proving that smart systems can evolve without sacrificing the standards that keep operations secure and effective. Everything we do centers on this exact principle. If you want to dive deeper into how this model works, you can check out ironwolf.igrecept.com.